In part 1 of my series on the all-metal transistor, I discussed the intriguing possibility of fabricating electronic and computing devices solely from metals without using any semiconductors. This concept could enable the creation of a device similar to the metallic robot Terminator depicted in Terminator 2 science fiction movie. As shown in the movie, all metal electronic and computing devices could offer extreme durability, withstanding significant temperature variation and operating under intense conditions such as high electrical currents and pressures. Today, I will delve into the potential and challenges involved in developing a light-emitting diode, or LED, using only metals without use of any semiconductors. LED made entirely from metals offer numerous advantages. First, the fabrication process for metals is far simpler than for semiconductors. Metals can function well in amorphous and polycrystalline forms, offering substantial benefits for integration in manufacturing. In contrast, high-quality single crystal structure is critically important for semiconductor to function. The simplicity of metal nanofabrication is particularly advantageous for 3D integration, where very difficult to maintain high single quality over the layers. The second merit is the high endurance for high current and temperature. Metals are famous for their robustness, capability of withstanding large currents and extreme temperatures. The third merit is the super scaling potential. All metals LED benefit from both lower contact resistance and bulk resistance, enhancing scalability and reducing energy loss. The fourth merit of all metal LED is faster operation speed. With metal inherently high electron mobility, an all metal LED could achieve faster operation compared to semiconductor-based counterpart. Can LEDs be made entirely of metals like aluminum or copper? For example, is it possible to fabricate an all-metal LED using principles similar to those of conventional semiconductor LEDs? Let's explore this intriguing idea. This is a structure of conventional semiconductor LED, which is typically composed of p-type and n-type region. When voltage is applied, holes and electrons are injected into a common region where they recombine, creating photons as the light output. A similar operation principle and structure can be envisioned for an all-metal LED. This design, illustrated here, features metal layers separated by thin oxide layers. When a voltage is applied across the structure, electrons and holes tunnel through the oxide layers between the metal regions. As they recombine in this metal, photons are emitted, potentially allowing for light output. As discussed in my previous presentation, metals inherently possesses both electrons and holes, enabling this all-metal LED design to mimic the operation of semiconductor-based LED. However, the fundamental question remains: will this all-metal LED design work? Under what conditions can it function effectively? Let's delve deeper into the operation mechanisms and challenges to understand the feasibility of this concept. This animation demonstrates electron-photon dynamics in direct gap semiconductors such as gallium arsenide. When a voltage is applied, electron energy becomes high in N region and low in P region. Consequently, electrons are injected into the conduction band from N-type layer, shown on the left, while holes are injected into the valence band from the p-type layer on the right. Alternatively, electrons are removed from the valence band into p-type layer, leaving holes behind. Since applied voltage is greater than the band gap, electrons are injected at energy above the conduction band minimum, while holes are injected below the valence band maximum. Rapid electron scattering within each band causes electrons to quickly move to the bottom of the conduction band and holes to the top of the valence band. When an electron transitions from conduction band to the valence band, it emits a photon with energy equal to the band gap energy and very small momentum. This process forms the basis of light emission in semiconductors LED. This animation illustrates similar dynamics in indirect gap semiconductor such as silicon, which does not produce light emission. In indirect gap semiconductor, the electron at the minimum of the conduction band have a different wave vector k or momentum than those at the top of the valence band. Due to the requirement of momentum conservation, band-to-band transition only occurs when an additional particle with sufficient momentum participates. The photon momentum is too small to fulfill this requirement, so a phonon, shown in green, which has a much larger momentum for the same energy, facilitates the transition. As a result, light is not emitted in this process. In order to understand dynamics in all metal LEDs, it is important to answer two questions about the electron dynamics in indirect semiconductor. The first question is, why does photon emission occurs only for electron transition from the bottom of conduction band to the top of valence band? Why cannot the transition happen from state in middle of conduction band, where there is a momentum matching for indirect semiconductor as it is shown by the red arrow? The reason is a very short scattering time within single band. The time is not sufficient to accumulate enough electrons for the population inversion. Additionally, the emission of photon requires some time. The second question is, why does direct band semiconductor emit photons while indirect band semiconductors emit phonons but not photons? It is because for the same energy, a phonon has a much larger momentum and wave vector than photon. The speed of sound is 300 meters per second in air, is much slower than the speed of light, about 300,000 kilometers per second. Consequently, for given energy, the momentum of phonon is about 1,000,000 times larger, and only phonon can require momentum for the electron transition in indirect semiconductor. The issue of photons' low momentum to energy ratio is a well-known challenge across various fields. For example, this problem restricts human ability to travel between stars. Currently, one of the most feasible concepts for interstellar travel relies on harnessing solar energy, as shown here. In this scenario, a group of satellites orbit closely around the Sun, converting solar energy into highly focused laser beams. These beams are aiming precisely at reflective mirror of the spacecraft, propelling it forward by transferring momentum without the need for onboard fuel. Also, the spacecraft's acceleration would be slow, it remains continuous, and over the course of a year, this could lead to a relativistic speed. However, two primary obstacles exist with this approach. One is the challenge on focusing a laser beam into a small spot over such vast distances. I think this problem is technically solvable. The second obstacle is due to a photon low momentum to energy ratio. Achieving significant momentum transfer requires extremely high energy laser beams, risking overheating and potentially melting the spacecraft. Even most of the laser energy is reflected by the spacecraft mirrors. One alternative solution to this limitation is to use electron beam for the initial acceleration phase. Electrons have a significantly higher momentum to energy ratio compared to photons, making them more efficient for imparting momentum without the need for excessive energy input. Let's return to the concept of creating LED entirely from metals. For instance, consider this LED made from copper. In metals, the Fermi level intersect electron band, meaning part of the band is filled with electrons while another part remained unfilled. When hot electrons and holes are injected from metal contacts on either side, they quickly move towards the Fermi level due to frequent inelastic scattering and recombine there without emitting photons. Therefore, in this case there is no light emission. It is because the rapid scattering within single band prevents creation of population inversion and a generation of a photon. Fortunately, most metals have two or more electron bands. In the example shown, the metal has a second electron band located at above the Fermi level. When sufficient voltage is applied, electrons are injected into the second upper band, while holes are injected in the first lower band. The electrons then rapidly descend to the bottom of the upper band, while the holes move up along the lower band towards the Fermi level. In the shown case, the momentum of the electron at the bottom of upper band and the electrons at the Fermi level of the lower band are different. As a result, a direct electron transition from the upper band to the lower band would require the existence of a phonon, a particle with sufficient momentum to satisfy conservation laws. Because a photon has relatively small momentum compared to a phonon, light emission does not occur in this process. Thus, in this case, still no light is emitted due to the momentum mismatch and the requirement of phonon involvement. The position of the Fermi level in metal can be modified by doping with other elements or by using low-dimensional structures. In this case, the Fermi level is adjusted so that the momentum of electrons at the Fermi level in the lower band aligns with the momentum of electron at the bottom of the upper band. When this momentum alignment occurs, electron can transition from the upper band to the lower band with photon emission, enabling light generation. This scenario demonstrates how laser emission could potentially be achieved in all-metal structure. Next, I will talk about tackling the issue of strong light absorption in metals. When discussing an all-metal LED, one significant challenge is the strong light absorption inherent to metals. Metals are well known as some of the strongest absorbers of light. This raises a critical question: what is the benefit of generating laser light inside metal if that light is immediately absorbed? At first glance, it seems illogical to fabricate an all-metal LED if the emitted light cannot effectively escape the metal. However, while it is true that bulk metals strongly absorb light, many optical devices are still successfully made from metals. For instance, the reflective coating in mirrors are made from metals like aluminum or silver. The second example is plasmonic optical devices. Plasmonic devices' overall loss due to light absorption is much smaller than you might expect. In fact, with proper design, the losses in plasmonic devices can be comparable to those in conventional metal-free optical devices. You can check my several YouTube videos on the technology of plasmonic devices for the silicon photonics. There are two key strategies used to minimize metal absorption in all-metal LED. As I just explained, the first strategy involves utilizing surface plasmons. Unlike conventional light waves that propagate through the bulk of material, surface plasmons are confined to the surface of metal. As a result, an electromagnetic field of the plasmon resides mostly in the adjacent dielectric material, with only a small fraction penetrating into the metal. This limited penetration significantly reduces the absorption within the metal, thereby minimizing plasmonic loss. The second strategy, focusing on blocking free electron absorption, which is primary source of light loss in metals. This type of absorption occurs when the conduction electrons oscillate in response to the electrical field of light. By designing structure composed of ultra-thin metal layers, like this, each less than 1 nanometer thick, separated by dielectric materials, electron movements perpendicular to the plane of the layers is sufficiently restricted. This configuration significantly suppresses free electron absorption when light propagates along the structure. An electric field is oriented perpendicular to the plane. By employing this technique, the light absorption in metals can be effectively reduced and therefore managed. As a result, the challenge of light absorption in metal does not present a significant obstacle to the successful development and operation of all metal LED. In conclusion, I hope I have convinced you that fabricating a light-emitting diode entirely from metals is indeed possible. Achieving this requires precise engineering of both band structure and Fermi level within metals. This technology is not yet available. I am optimistic that it could become viable in the near future. A fully metal-based LED may offer unique features that are not possible with conventional semiconductor LEDs. Its distinctive performance and potential durability could introduce substantial benefits across a range of technological applications like this. Thank you for watching.